In section 11.4, we're going to talk about a special type of infinite geometric sequence. If you recall now, geometric sequences are exponential functions, and if you recall, we dealt with exponential growth, a graph of which would look like this. You can see that as I approach positive infinity, my values approach positive infinity, so they become infinitely large. There's no way you could ever find the sum of this kind of an infinite series, right? Each new term becomes increasingly large, so there is no way to derive a sum from this. On the other hand, when we dealt with exponential decay, as I approached positive infinity with my inputs, my graph approached 0. So each new term in this case has less and less impact on the final sum. So we actually can find the sum of infinite geometric sequences if and only if we're in an exponential decay model. So to find out which situation we're in, we want to take a look at R, the common ratio. And if the absolute value of the common ratio is less than 1, then we can use this formula that the sum of an infinite sequence is equal to the first term divided by 1 minus R. Right? I'm going to do the second example first because I want to talk about the first example for a couple of reasons. So here I know that my first term is 3, and I know that my common ratio is negative 1/2. So if I plug into this, the sum of my infinite series will be equal to my first term, 3, divided by 1 minus negative 1/2. All right, and so then if we go ahead, this is 1 minus a negative number, so that's 3 divided by 3/2, 1.5, and that would be 3 times the inverse of this, 2/3, which would simply be 2. Okay, so the sum of this infinite series, if I take absolutely every term, add them all together, the sum will be 2. Okay? Now, this one's a little sneaky because you'll see, this doesn't ask me to go from the first term to infinity. It's asked me to go from the 0 term to infinity, so there's an extra term. And also you'll notice up here that this is not I minus 1. This is not an explicit rule actually in standard terms. Right? So at first glance you might say, oh well, my first term is 3 and my common ratio is 2/3, but if you plug 1 into this and check for the first term, you won't get that value. So the first thing I want to do is find out what is a sub 1. So 3 times 2/3 to the first power is actually 2. So 2 is actually my first term. So if I wrote this correctly, it would actually be a sub n is equal to 2 times 2/3 to the n minus 1 power. Okay, so that's a difference, and I need to be aware that sometimes the book will be a little tricky with what it shows me. Now if I plug that value in here, this will give me the sum of the infinite sequence, but again that's from the first term to the infinite term. I'll still have to go back and find the 0 term. Right? So I'll take my first term, 2 divided by 1 minus 2/3. So that's 2 divided by 1/3. Dividing by 1/3 is the same as multiplying by 3, so my sum will be 6. But I've got to go back now and find the 0 term. Right? So when I plug in 0, in either one of these I can plug in 0. 2/3 to the 0 power is 1, times 2 is 3. So that'd be plus 3. And so my actual sum from the 0 term to the infinite term is 9. So this is the sum from 1 to infinity. This is the 0 term, and when I add them together I get this new value. Okay, so this problem was very straightforward. More of the type of thing you will see on an assessment from me. This is the book sneaking in a problem that looks like it's in standard form, but it's not. And you have to make some alterations to put it in standard form so you can identify a sub 1. and then move forward. Does that? So that's our situation. Okay. So keep an eye out on the problems being supplied to you by your book because they can be a little confusing. Continuing on, I may have something more straightforward where they're going to give me the sum and a sub 1, and I'm supposed to find r. So 6 is the sum of the infinite series. A sub 1 was 2 over 1 minus r, and if I want to solve for this, I'm going to multiply both sides of the equation by 1 minus r. So over here I'll get 1 minus r, and I'm going to divide by 6. As you see, by doing those two steps, multiplying by this value, dividing by that value, they basically just switch places. Right? 2 divided by 6 is 1/3. So now I have 1. I'm going to add r to either side. Is r plus 1/3. And if I subtract 1/3 from either side, I'll get 2/3 is equal to r. Okay, so by supplying me with the sum of the infinite series and a sub 1, I'm able to find r. Another thing you can do with this formula is turn repeating decimals into fractions. So what you want to look at, the first thing you have to determine is how much of the decimal is repeating. And here I have a 1-digit repetition. So you could see that actually if I took 0.77777 and broke it down into things that were being added together one place at a time, this first digit is 7 times 0.1. The second is 7 times 0.1 squared, or by 0.01. The third one is times 0.1 cubed, 0.0001, and so forth. And this then fits the pattern of a repeating, this then fits the pattern of a geometric sequence, okay, or a geometric series. So in this case, I can see that what's my first term? It's 7 times 0.1, or 0.7. And I know that my common ratio is 0.1. And if I go ahead and plug those values in, I have 0.7 over 1 minus 0.1, which gives me 0.7 over 0.9, which is equal to 7/9. Okay, it's a little more complicated as I have extra digits in my repetition. So you can see that this is 0.23, right? It's 23. My first term, a sub 1, is 23 times 0.01. Right? It's actually 0.01 that is going to be my common ratio. So the key here is you're matching the number of decimals in your portion that repeats with the number of decimals in your ratio. Right? When I go through that, I'll get 0.23 over 1 minus 0.01. That becomes 0.23 over 99. So this is 23/99. Okay, so this is just taking a repeating decimal and turning it into a fraction.